Hello everyone, I am Woojin Lee. I'm a researcher at ATRI and this work was done at Konkuk University. Today, I'm excited to present our paper, Do Large Language Models Have Emotion Neurons? We dive deep into LLMs to ask, when a model responds to emotions, are there dedicated neural circuits inside? Let's explore our systematic investigation to find and test these emotion neurons. Our research starts from a foundational study by OpenAI in 2017, including Ilya Sutskever, which discovered the sentiment neuron. This single neuron learned to distinguish positive and negative reviews without supervision. This was a powerful proof of concept, showing that interpretable units can emerge in complex models. It led us to ask, can this scale beyond a simple binary axis to a full spectrum of human emotions like happiness, anger, or fear? This brings us to our core idea. We're not just looking for neurons, we want to test their function by manipulating them. Imagine feeding the same happy dialogue into a llama model. On the left, in the normal condition, happiness neurons fire, and the model correctly predicts happiness. On the right, we artificially mask these happiness neurons. Our hypothesis is that the model, unable to use its primary circuit, falls back on a secondary signal, like surprise, causing its prediction to shift. This design allows us to prove the causal law of these emotion neurons. To formalize this, we structured our work around three research questions. RQ1, existence. Do these emotion neuron groups actually exist? RQ2, functionality. What happens when we manipulate them? This aims to establish a causal link. And RQ3, granularity. How does the impact change depending on how many neurons we mask and where they are located? This forms the roadmap for my talk. To find these neurons, we first needed the light data. We built our own high-purity synthetic emotion dialogue dataset in 3 steps. First, topic augmentation. We expanded 315 topics to over 5,000 for diversity. Second, dialogue generation. For each topic, we generated dialogues for one of the 6 basic emotions. This gave us a massive initial pool, but quantity isn't enough. So, third, multi-model filtering. We used 3 different models as judges. A dialogue needed at least 3 out of 4 agreements to be included, ensuring high emotional purity. This gave us a robust dataset for our analysis. After filtering, we were left with nearly 300,000 high-quality dialogues, well distributed across the 6 basic emotions. On the right are a couple of examples for happiness and surprise. With this robust dataset, we were led to identify the emotion neurons. So, how did we find them? We developed an entropy-based method. First, we feed our dialogues into the model and observe neuron activations. Then, for each neuron, we calculate its activation distribution across the 6 emotions and find its entropy. A neuron that selectively fires for just one emotion will have a low entropy. Based on this, we selected the top 1% of neurons with the lowest entropy for each emotion. To ensure validity, we identified neurons on 95% of the data, but all our functional analysis were done on a completely unseen 5% test set. Now for our findings. For RQ1, do emotion neurons exist? The answer is a clear yes. We identified distinct neuron groups for all 6 emotions in both llama models. These graphs show their distribution across layers. It's not random. There are clear peaks, and the pattern changes with model scale. In the 70 billion model, the distribution is broader and starts earlier. This suggests larger models process emotional information in a more distributed fashion. So, emotion neurons are rare. For RQ2, are they functional? The results are complex. Some neurons are critical. For discussed in the 8 billion model, masking its neurons causes accuracy to plummet. This means they are irreplaceable. We see the same for surprise in the 70 billion model. However, for happiness, masking causes almost no performance drop. This suggests its function is more distributed or other neurons can compensate. So for RQ2, yes, they are functional, but their roles differ. From irreplaceable specialists to members of a complementary system. For RQ3, we looked at granularity. First, the number of masked neurons. For surprise, we see a stark, dose-dependent response. Masking just 1% causes a huge performance drop. This means it relies on a core set of neurons. In contrast, disgust is much more resilient, reinforcing that some emotional representations are more robust. The key takeaway: sensitivity to masking is not uniform and varies by emotion. We also investigated the location. Does it matter where the neurons are? Absolutely. For surprise, masking the middle layers has a much stronger impact than masking the bottom or top layers, suggesting a functional hotspot. For most emotions, masking all layers causes the biggest drop, confirming that emotion processing is a distributed, multi-stage process. An emotion neuron's importance depends on both what it is and where it is. To conclude, let's summarize what we've learned and where this research can go. Our investigation has led to 3 key takeaways. First, emotion neurons are not just a metaphor, they are identifiable and functionally critical components within LLMs. Second, emotional representation is a complex system, featuring both irreplaceable specialists and complementary overlapping networks. And third, this process is multi-layered, with different layers playing distinct roles. Of course, our work has its limitations. First, we focused on the 6 basic emotions. A natural next step is to investigate if specialized neurons exist for more nuanced states like empathy or sarcasm. Second, our study was confined to the text domain. How these emotion neurons behave in a multimodal context, responding to vocal tone or facial expressions, remains a fascinating open question. Ultimately, we believe this work is a foundational step towards building AI systems that are not only more capable but also more transparent, interpretable, and genuinely emotionally aware. Thank you very much for your attention. See you in Vienna. Bye.